Can you hear me? Okay. Um, so let's start by mentioning that yesterday night was the deadline for the homework to be delivered. And I want to be clear on the fact that those of you who delivered the homework this morning, I mean, if you delivered it around midnight and a half, 1 a.m., it's still fine, but not this morning. So those of you who did that will just receive it back with 0 points. Um, okay. Okay, so let's start from where we left. But before that, let me recap a bit what we have done so far. Um, so we have seen a bunch of methods for model-free, value-based reinforcement learning. And in that group, we have methods like Monte Carlo methods, temporal difference methods, like SARSA, Q-learning, TD0, expected SARSA, and so on and so forth. We have seen also some intermediates between these methods that include, for example, n-step bootstrapping methods, um, where you can have more sampling or more expected updates. We have also said that a bunch of these approaches can apply or can have similar methodologies in the model-based land, where instead of doing just active reinforcement learning, where the agent acts in the word and then tries to learn a value function and from this to derive a policy, there is also another step where the agent tries to learn a model, and on top of this model, some planning process is executed in parallel to the active model, sorry, to the active reinforcement learning approaches. Um, then we came back to say, okay, now what if instead of using tabular approaches, which is the ones that we have described in all classes so far, we wanted to use a function approximator? Well, for approximating, for example, the value function. Well, in that case, we have introduced a bunch of methods that allow us to pre-process the state in such a way that learning on top of this, it's somewhat manageable for the function approximator itself. And this actually applies to value-based methods, but even more to policy-gradient methods. That is what we have started introducing last week, but we'll go a bit deeper into it today. So what are policy-gradient methods? Policy gradient methods are substantially different from value-based methods, because instead of learning a value function or an action value function and deriving from it a policy, we directly learn a policy. So we directly learn a mapping from states to actions. So instead of having a parameterized value function, or maybe we can also have that, but we have another element here, which is a parameterized policy. To further clarify this concept, what's again the difference between value-based methods and policy gradient methods? In value-based methods, we typically compute and learn the value function, and from this we do an argmax. We do the argmax in order to choose what is the best action. In this case, we can just directly use a policy, and pass in the state to the policy and compute what is the action that should be executed in that specific state. So there is no more consultation of a value function, although a value function could still exist somewhere, and we can see how this is going to be used. And note that, as I was saying before, the value function can be learn itself, so it can be another function approximator where it has some other parameters that we can say are maybe the weights or a neural network or whatever. Um, so how do we learn directly a policy? Well, by simply performing gradient ascent on a performance function, or a gradient descent on a cost function. This performance function is typically denoted in reinforcement learning as j of theta, because it depends on the parameter of the policy, of course. And I mean, in practice, we don't have the true performance function, but we have an estimation of that, so a stochastic estimation of it, which in expectation will approximate the true one. So also the gradient in expectation approximates the true gradient of the performance with respect to the parameters. So methods that do these kind of things are policy gradient methods, and we'll see that in order to compute this gradient here, there needs to be some introspection in what the policy is actually doing. So we'll see some formulas today, which will seem complicated, but we can spend a lot of time on them if you want. So if you have questions on those, please ask them, because I reserved basically 2 hours to understanding these concepts today, which are very important. I've been repeating that the policy is parameterized. You can parameterize that in any way that you want. It can be a linear function, so you have the weights that represent the multiplicators of your parameters, or otherwise you can use a function approximator like a neural network, or something that might be nonlinear, or you can also do some other thing that you can think of. The only important thing is that this policy is parameterized, and it must be differentiable with respect to its parameters. So that this element that we see here, this gradient of the policy, uh, given a certain state and its parameter exists, and it's finite. So the practical requirement for this is actually that the policy never becomes deterministic. So why do you want to do that? For sure, because this allows us to explore. If the policy becomes quickly deterministic, then exploration is done. Why? In this case, we are removing the epsilon component in the epsilon greedy, because we are not acting greedily with respect to a certain um, value function. What you could do if your policy is deterministic, in practice, there are methods that are still policy gradient methods that have deterministic policy. So you will see in your projects, there will be an algorithm that is called DDPG, which is deep deterministic policy gradient, in which, as the name suggests, you have a policy which is deterministic, but you force it while learning to not be deterministic by adding some noise. Specifically, they add some Ornstein-Uhlenbeck noise, which is a specific kind of noise. But again, during learning, you don't want to be deterministic, because you want to ensure exploration. Let me see if there are questions on this. So the answer is probably yes. I will send a message for confirmation this afternoon because there is some coordination that is happening with Professor Yoki as well, and I have to talk to him like right at the end of this lesson. So I'll post a message um, on Classroom to let you know if that is confirmed. For now, assume that it is confirmed. Let me resolve this question. Okay, so in the case of a value function method, we have said we do argmax over the action value function, we choose what is the best action. How do we select an action in the case of a policy gradient method? Typically, what you do is using an exponential softmax distribution, which we have already seen, if you remember, when we talked about bandit problems. And this exponential function is based on a preference function. This preference function can be any kind of preference function. So, for example, can be linear in the feature, as I was explaining before, or can be a neural network. So the parameters are the network of the weight in the network weights in this case, and so on and so forth. Um, why do you want to have an exponential softmax distribution? Of course, is because the policy will never become really deterministic, but can become very close to be deterministic, while the epsilon greedy methods approaches cannot do that, right? Because you have still a limitation in your epsilon, unless you're manually decreasing the epsilon every time, but still there is not, I mean, there is a limit to that in the sense that it cannot go as close to being deterministic as something like this can. Uh, also, this enables selection of actions with arbitrary probabilities, and you can inject in this preference function some prior knowledge if you have the possibility and the skill and the knowledge to do that. So all in all, we have seen some examples last week, but why do we want to do something like this? So learning directly policy compared to learning a value function, then deriving from it a policy. Well, this is one example that we have already seen. It's not really an example, but is a motivational example. If you have problem with the even with a discrete action space, but with a large discrete action space, then you need to compute the Q value for every action and then to do the argmax on that, which can be quite expensive, and it can be more complex than just consulting a policy that will tell you exactly which action you should do for that specific um, state. So this is the last situation is what happens in policy gradient methods, while the first situation that I have described is what happens in methods like Q-learning or deep Q-learning, or more in general with action value-based methods. um, even more than that, there is a structural problem um, doing an argmax compared to using a stochastic policy, which results in the fact that the policy is going to oscillate much more for very small variations in the value function. So let's look at again at this scenario where you have a short corridor, and in every step of this corridor you get a -1 reward, so a negative reward. You have two actions which are right and left, And um, the actions, so this is a stochastic scenario where the actions are actually correct in every state. So if you go left in the starting state, you will go left. If you go right in the starting state, you will go right. But in the and this is the same also in the third state, and the fourth state is a goal state, so it's a terminal state. But in the second state, you have a situation where the actions are reversed. So if you go right, you will end up going left, and vice versa. Now, let's assume that the featureization of these states is identical, whatever is the action that you're taking for every state. So if you have right, uh, and in a certain state, then your representation featureized will be 1, 0. And if you're going left for every state, then your featureization is 0, 1. Then it's basically impossible for the agent, given that the featureization is the same for every state here, to discriminate between the states. And so understanding what would be the basically understanding that in this second state the action should be uh, different. So let's consider what happens in a um, value-based method. So in a value-based method, we'll have the value function that will be probably oscillating around here while learning as a function of the fact that you are being uh, epsilon greedy with respect to the value function. So in the moment when the uh, uh, epsilon greedy policy is going left, right? Because the value function will be leaning towards the left side, and it will be epsilon greedy with respect to that. The agent will go and end up with a reward, with a performance represented by the total value accumulated in a certain number of episodes, in this case on average, so in expectation. um, it will end up with this kind of performance. If it goes right, it will end up with this kind of performance. But all in all, the optimal policy in this case would be to not commit either to go left or to go right, but to be stochastic, meaning that it's not enough to go right with probability 0.1, for example, if we set epsilon to 0.1, or to go left with probability 0.1, because you should really do a stochastic decision where the probability is of going left and right is almost 0.5, except it's leaning a bit more towards the right, because first of all, you have two states that are because you have two states that are that have the correct action being executed, and one single state where the actions are reversed. So as you can see, if we commit to a specific direction in the by doing dr max, which is the best that we can do, right? If we rely on an action value based method, the best that we can do is being greedy, which means choosing one action, and being epsilon greedy in this case, which we want to be in order to not be at the uh, uh, bottoms of this performance function. Um, However, that's not ideal anyway. And also consider that if the policy, if the value function is at this point oscillating between 0.51 and 0.49, this being greedy will result in the fact that the policy will dramatically change from going always left to going always right, and vice versa, which um, which suggests that the policy is more unstable for certain domains compared to a policy gradient method. Questions on this part, if there are questions? Approaching deterministic means that the policy is not deterministic, but the probabilities for all the other actions are very small, except for one, which is the action with the highest probability. You can think of the probability of that action being 0.999 and all the other actions having 0.001 divided by the number of the other actions, for example, which is not deterministic, but and still ensures the possibility of doing some small exploration in that case. Hmm? Other questions? Is it clear why the policy is a bit unstable in this setting if you do an action value based method instead compared to a policy gradient method where you directly learn a stochastic policy? This concept, which concept? Are you referring to this example or to the near deterministic? Okay, this example. Again, so these states are basically undistinguishable for the agent because their featureization is the same. Is 0, 1, 0, and 0, 1, only depending on the action. Okay. Now, what happens is that if you use an action value function, you will do argmax of this action value function, which will for a certain state an action, right? But the problem is that if you do that, you will always commit to either going always left or going always right. Or at the best that you can do is, instead of being greedy with respect to the value function, in this case, is being epsilon greedy, which allows you to sometimes go to another, to the other side. So to go right instead of left and left instead of right. But actually, this is not enough because the the optimal behavior here is being really stochastic and almost tossing a coin to decide whether you should go left or right. Or actually, you should go right with a bit more frequency compared to going left, just because there are two states here that have the correct action execution and only one state that has the inverted action execution. But the agent cannot distinguish between those, right? So it needs to go in a stochastic way. Yeah, this is the first issue. The other issue is that if you are learning the value function and the value function is oscillating for the value exactly because there is this uncertainty here between, for example, I don't know, being a bit higher for going right and going a bit um, higher for going left, then when the value function is oscillating at that point, the policy is changing dramatically from going always left to going always right, which means that the policy is much more unstable compared to policy gradient method, where you are directly optimizing for the performance and you are being stochastic, and you can, I mean, the policy is not changing so dramatically, at least. I hope this was clear. Okay. Another important thing to take into account for policy gradient methods is that they typically have better convergence properties compared to value-based methods, which is also what I was mentioning before. So while training, value-based methods can have big oscillations both in the value function and as a result in the policy, which results in a bigger oscillation also in the value function. So if this is the case, it's better to directly be optimizing a policy, because the policy gradient methods just follows the gradient of the performance to find the best parameters, which is guaranteed to converge at least to a local maximum, or ideally to global maximum. The problem is that often this converges only to a local optimum, which is a general problem anyway of function approximators. So even if you're learning a value function with a function approximator, you might end up in a similar situation. Okay, so now let's go a bit in the theory of this. So let's consider an episodic setting where you have no discounting to start. So this means that we are just summing all the rewards without the discount factor in order to estimate our value function. So if we have this set up, then we can define the performance as just the value of a certain start state, which is the start state of the episode. Right? So V pi theta, so the value of the policy that depends on the parameters theta, starting in state 0, will be the true value function for the policy with these parameters theta, which is why we can use this as our performance function. Of course, the performance depends on a bunch of things, which are not only the action selection, but also the state distribution. The state distribution is affected by the policy parameters as well the action selection, as well as the action selection. Okay, so given the state, the effects of the parameters of the policy can be easily computed, right? So the problem is more on the side of the fact that because we compute the action, and so in that case, it's easy to compute what is the effect of a certain policy. The problem is more on the state distribution, because that depends also on the environment. So this is one complication, and because the state distribution is typically, I mean, the effects of the environment are typically unknown to the agent, because we are in a model-free setting. We don't have a model unless we're doing model-based reinforcement learning, and even then, it's still learned. So we don't have the true state distribution, because again, the action selection depends on the policy, and given a state, we can compute the action, so the effects of the policy parameters are quite clear in that. But the state distribution, which still depends on the sequence of actions that the policy has taken, right? This still depends on the policy, and it's important to compute the performance, but we don't know how to compute that in a clear way, because this depends on the parameters. When I say we don't know how to compute that, I'm referring to the fact that we didn't know this theorem before when we were talking about this, which is the policy gradient theorem, which is giving us some answers on how to deal with this unknown part. And now we are starting with the pain, so with the formulas. So again, I will check on Slido quite often. Please ask questions if anything is not clear, because we need to understand this. So Policy gradient theorem. What is the policy gradient theorem? The policy gradient theorem gives us an analytic expression for computing the gradient of the performance. Why do we want to compute the gradient of the performance? Because we want to do gradient ascent over the performance, and the formula for doing gradient ascent over the performance is the following. So the next parameters, so the parameters like the next iteration will be the parameters that we currently have plus alpha, as usual, that multiplies some derivative, which is the derivative of the estimation of the stochastic estimation of the performance. So assuming we have the true performance for now, how do we compute this gradient given that there is a complication that this performance here depends on the state distribution? So this theorem tells us that the gradient of this performance function is proportional to the sum over all the states that where we multiply for every state mu, which is the on-policy distribution under the policy pi. What is the on-policy distribution under the policy pi? It's the basically the distribution of the states which is generated by the policy, right? On-policy distribution is the states that the distribution of states that the policy in expectation visits under its current parameters. And this on-policy distribution multiplies the sum for all the actions of the value of the action value function, basically for the policy given the state and the action that we are taking into account in that specific case, that multiplies the gradient of the policy. Okay, so we'll see now more in detail what this is, but this is telling us that basically we are taking into account the state distribution. We are taking into account the value of every state and action multiplied by how the policy is changing. Okay, the derivative of the policy. Okay. So what is the on-policy distribution? As I was saying, is the distribution of the states that the policy visits, which you can abstract in your mind as the fraction of time that is spent in a certain state for all the states. So in continuing tasks, this is a stationary distribution that depends on the policy pi. In episodic tasks, this depends on the initial state, for sure, and also on the distribution under pi. So if we have these two elements, which are h and eta, where h represents the probability of an episode beginning in a certain state, and eta is the number of steps spent on average in a single episode, then we can compute the time spent in a certain state as the probability of starting in this state plus, right, the sum for all the states of the time spent in this state that multiplies the probability of transitioning in the state that we're interested in. Basically, we are considering all the possible states that would transition in the state that we're interested in, and so the probability of transitioning in there multiplied by the probability of being in those states that would transition in the state that we're interested in, plus the probability of beginning in the same state, which is, I mean, quite obvious, right? So we the, the probability of being in a certain state is computed as the probability of starting there or ending up there because some other state leads you there. Now, this is making use of the transition function, which is unknown uh, to us. We'll see how we are getting rid of all of this. Uh, so how do we get rid of this? Is often also just counting from the samples that we have. So if we can count the number of times that we have visited a certain state and then we have transition in a certain state, then we can do this computation over here. The final computation of the of this mu term then will be just making this a probability. So it's just dividing by a normalization term. Questions so far? Okay. So hopefully this part is clear. So this is just giving us a formal definition of what the on-policy distribution is. Now, if, as we said, the performance for us is the value function, how do we compute the derivative, the gradient of the state value function? We can do this by basically expanding everything and writing it in terms of, we can start by starting to write this in terms of an action value function. So the gradient of the value function here will be, and this is a definition, right? So this is one definition of the value function, is just sum for all the actions of the action value function multiplied by the probability of the policy of choosing a certain action in a certain state. Now you might complain here that there are two definitions of the value function. So there was few slides ago, you have seen that the value function is the maximum over the queues for that specific state and all the actions that you can consider. And that is true. It's not a different definition from this. That is true in the case when the policy is greedy. So if the policy is greedy, then this is going to result in the same thing, because you are doing, instead of doing the argmax, this will go outside, and then so in the policy you're doing, instead of doing the argmax, this is going to be replaced by the fact that you're using a maximum here, and it's the same thing. This is because the policy would be greedy. If the policy is stochastic, like in the case that we're considering, then we should consider the full, basically the full expectation on the policy of getting a certain value. This is why the formula seems different, but it's the same formula still. Okay, so now what if we want to compute the derivative of this? Then this is just a product. Then we can compute this as the derivative of the first term that multiplies the non-derivative of the second term plus the non-derivative of the first term that multiplies the derivative of the second term. Okay, so if we do this, this will result in this object over here, which we can further expand in this. So if you look at this second step, we are expanding q pi as being simply the reward plus the value under the policy of the next state, right? Which is basically the definition that we can use also because here there is no discount factor. As we said, we have no discounting, so this is exactly a correct definition of what the Q function would be. Multiplied, however, by this probability of transitioning in S prime and obtaining a certain reward given S and A. So this is the transition function. Now, from here, we can remove R, the reward, which is just a constant, right? So we don't care about that in the derivative because this will be 0. So we remove everything that concerns the reward, and we're left again with the transition function that multiplies the derivative of, again, v pi, but in s prime. So we can further expand this further and further, and this will be basically resulting in the probability, on its notation here, you see the probability of transitioning from S to another state X in k steps under the policy pi that multiplies the gradient of the policy and the action value function for that state and the action that we are considering, because here there is a sum over all the actions, so we are considering all the possible actions. Okay. So the gradient, what this is telling us is that the gradient of the value function under a certain policy pi depends, of course, on the transition function, as we imagined even before looking at this formula, and the action value function that multiplies how the policy would change according to the change of its parameters, right? What this is the gradient, what is telling us. Okay. Now, we can plug this in our derivative for the performance function, which we said is the derivative of the value function if we start in S0, right? This is what we said from the beginning, right? So here we said we define the performance as the value of the start state, of starting the state, sorry, in episode of the episode in S0, of starting the episode in S0. Then if we replace this here, we're saying instead of having this general definition here, we don't need to consider, we are considering basically directly as 0 in the fact that we are starting from S0. So this formula plugs in here as 0. And this is basically, what is this basically for us? It's exactly eta, right? This is the same thing, right? Because eta will be the number of steps spent on average in S in a single episode, which is exactly considering the probability of transitioning in a certain state and the probability of starting in that state. So that's exactly what we are looking for. Okay, now we're doing some simple mathematical operations here. Here we are multiplying and dividing by the sum of eta in S prime, right? We're multiplying and dividing here. So this becomes mu. So we are left with this object over here, and we are left with the usual product of the Q function that multiplies the gradient of the policy. And so we can just say that the gradient then is proportional to this mu that multiplies sigma, that multiplies the gradient of the policy and the Q function of the policy. So we'll see a specific instantiation of this, but questions, I hope there are questions, because this means that you have been following. I'll give you some time here to ask questions. So is this perfectly clear? I guess. I mean, I don't have any feedback in the room today, so I cannot even see a face. So please give me some feedback. If it is not clear at all, we can go through this again. We can try to clarify any doubt. Okay, 25, slide 25. Okay, so theta represents for us the number of steps that are spent on average in S in a single episode. So that is, in practice, the time spent in S, either if you start from there or you transition there, right? So how, so this is H is telling us if you start there, and this other element here, this second term, is telling us if you transition there. So the probability of transitioning there, basically, or the number of times you transition there, which if you normalize that is going to be the probability. But anyway, the number of times you transition there is given by the transition function that multiplies the policy for any state that would have the possibility of transitioning in the state that we're interested in, right? So multiplied by the probability that the policy would select an action that would actually lead to transitioning there, multiplied by the frequency with which you are visiting the state that eventually would allow you to transition in S. Right? So this is the part that says you are starting here. This is the part that are saying um, this is considering the probability, the number of steps that you are visiting S prime, and S prime that would eventually transition in S if the policy would select an action that would lead to S from this S bar. Okay? Then mu is just the normalized version of it. And if we don't have the probabilities, we can just do counting over these states and compute this object over here. So this can be computed, right? Other questions? So this is basically the most difficult part. If you understand this, which is a recursive computation, it's then quite easy because at this point you are just defining the gradient of the value function as in the form of the action value function that multiplies the gradient of the policy that multiplies this object over here, which is the probability of transitioning from S to K to X in K steps under the policy. Now, if we assume that our episodes are starting from S0, then we can just replace this into here, which is exactly what eta is giving us. So the number of steps that we spend on average in a certain state S for all the states, simply. Then here there are just some mathematical tricks to get to get something that we can use in practice. And the fact that this is proportional is just because in the gradient we don't care about any other proportionality element. Okay, so let's look at one specific example, one algorithm that makes use of this, which is reinforce, which is basically the Monte Carlo, it's a Monte Carlo-like approach in the policy gradient. So it's a Monte Carlo-like approach because it uses full episodes in order to compute its updates. So how do we get to this algorithm. So we want some samples in such a way that the expectation of the sampled gradient is proportional to the actual gradient of the performance measure. And so we, first of all, can do that by considering a small constant proportionality step size. The policy gradient theorem gives us the exact expression to compute this gradient. And we basically only need a way to sample this object over here in expectation, right? So we want something that approximates this expression and something that we can sample from. Um, so now, given that this is the on-policy distribution, we can replace this sum over here by an expectation, right? Because the policy is giving us exactly this. So if we sample from the policy, right? So if we are sampling from the policy one episode, or actually more than one episode on average, this will be giving us exactly this. This will be giving us exactly this object over here in expectation, right? Because this is the on-policy distribution. This is how we started, right? This is where we started from. So if this is the on-policy distribution, then just by sampling from the policy, we can get rid of this object over here, and then this will take into account for the on-policy distribution if we are following the policy for a bunch of episodes. And then we can just use directly this object over here, right? The sum over all the actions of the Q function for a certain state multiplied by the gradient of the policy, and instantiate the gradient ascent um, uh, problem from this. So we're just using samples. In expectation, this is approximating the true gradient. Now, Q hat here will be a learned approximation of Q pi, right? So it's this is why we have W over here, which means that we are not using the true policy value function, but will be a learned approximation of this. And we are using a function approximator here because we are assuming that tabular methods here cannot be used. So if we massage a bit more this formula, you will see that basically we can multiply and divide by the policy itself, so the probability of taking a certain action in a certain state given the parameter, given a certain state and the parameters of the policy. And if we do this, we can also get rid of this term, right? Because uh, the policy is taking care of this. So the expectation in the policy is taking care for us of this, right? So this is already in here in the expectation. So we can get rid of this term. So we are left only with the action value function that multiplies this gradient of the policy divided by the probability of taking a certain action given a certain state and the parameters of the policy. Now, what is this term? If you further look at this, in expectation, this is the return, right, that you get from by taking from the state by taking this action and then continuing according to the policy. So this is exactly the definition that we have of the action value function expectation. So we can further simplify this and use sample updates. We can use our samples over here. Actually, this other object here is the gradient of the logarithm of the policy, so of the log distribution of the policy. So this is telling us that every increment, every update that we are going to do will be proportional to the product of the return. So if the return is higher, this update is going to be higher. Remember that the return is the sum of the of the reward that we get until termination, and this is why this is a Monte Carlo method, because it waits for the end of the episode to compute the return, and then we do this update following the return. And then this multiplies the gradient of the probability of taking a certain action divided by the probability of taking it. What does this mean in practice? So this is the direction in the parameter space that most increases the probability of taking that action in that state. Huh? And this is, of course, if the this is inversely proportional to the action probability. So in this way, if the action is not so frequent, then you are having a bigger update over here in order to not give an advantage to just frequent actions, right? So the full pseudocode of this is just generating an episode, and for each step in the episode, we compute the return, and for each of these states that have been visited in the um, um, in this episode, we do the update proportional to the return, and this is, as I mentioned, the gradient of the logarithm of the policy. So we're using directly that. Questions? While we wait for some questions, you can see here the performance of reinforce when we are changing alpha. Of course, alpha is going to be our learning rate here. So this is an average over 100 runs of the algorithms. And so you will see that the learning rate highly affects the performance. If the learning rate is going to be too high, then you're converging too quickly to uh, some some policy which is not correct. If we are doing a small gradient, small learning rate, then the policy is just converging more slowly. So you need to manually tune this, and this is a common issue in any machine learning problem. I see no question. I hope this is clear, and if not, you're going to ask questions. Um, so this policy gradient theorem that we have seen can be generalized to include a baseline, and this is something that we have seen also in the case of the bandit problems, right? So a baseline can be any function where the sum of the baseline over all the all the actions is 0. So if we do that, the update rule for reinforce becomes just alpha that multiplies the return minus the baseline, and this is the usual gradient of the policy divided by the policy itself. So this is a generalization of the reinforce. So the expected value of the update is generally unchanged, but it's a generalization because the baseline can reduce the variance, as we have seen for the bandit problems. Here, in the bandit problems, the baseline was fixed. Here, the baseline changes with the state. Because, for example, some states have a higher baseline because all the actions have high value. So the natural choice for a baseline is an estimation of the state value, which can be learned itself. So we have three things that we learn in this case, which is the state value function, the action value function, and the policy. we can learn this using, for example, any Monte Carlo method that we have seen before in for learning the value function, also for learning the action value function, and then we plug that in here so that we compute our delta here not only as the return, but the return minus the value function, which is, again, the value function is defined. How is it defined? Where is the formula? Here. Is defined as the action value function that multiplies the probability of taking a certain action in a certain state. So this is a it's an expectation, right? It's a sort of weighted average, depending on the policy, of the action value function. So basically what we're doing by having uh, the baseline here is that while G for us here is allowing us to compute in expectation the action value function, here we are subtracting the average action value function. So we are basically saying, I want to center all my action value functions in 0, removing the average, and then I'm just looking at how these are oscillating. So this is removing some variance in our optimization process. So basically, the algorithm is the same now, except that we are using this delta, where delta is computed as the return minus the value function. That we are also updating the weights of the value function itself. So if you look the same task that we were looking at before for the plot, which we don't care what is the task specifically, we're just comparing the two, we can see that reinforced with baseline converges much faster to a better performance compared to reinforced alone. Guys, questions? Okay, anyway, so policy gradient methods open for us the possibility to basically have some sort of intermediate between action value based methods and uh, uh, policy gradient methods. And these methods are specifically called actor critic methods. Actor critic methods are basically different from reinforced with baseline, although they are similar in the sense that reinforced with baseline will converge to a local minimum, but it's based on a Monte Carlo update. So tends to learn slowly, as we have seen already for the value function methods. And it's inconvenient for line or continuing problems. So what we can do is, instead of learning in a Monte Carlo way, we can learn in a TD way. We can use a sort of temporal difference method where we use bootstrapping for learning the value function, and the state value function is using a critic where, so the critic here is the value function. So the value function acts as something that is correcting the policy, which is why it's called the critic. And the actor, which is the policy, who is acting, is corrected by looking at this critic at every state. Note that the state value function in reinforced does not do any bootstrapping, and it's not a critic because it's not used to do update at every steps. It is used to do updates after the full episode. So here, if we look at one-step actor critic methods, we're basically replacing the full return that we have in reinforce with a one-step return, which will be just the reward plus gamma that multiplies the value function. So this is the standard TD error, one TD error, TD0 basically that we have seen. And this is now our delta. As you see, the formula is always the same. We're now replacing the delta. As we used to replace the target in value-based methods, we're now replacing the delta. Instead of being the return minus the value function, it's the uh, TD error. So um, this is how we're going to compute that. We compute our TD error. We use this to do our update of the value function, and we use this to finally we do the same in order to do the update in the um, policy itself. So it might be the first time that you see this specific formula for the both in reinforce and in actor critic method. It's the first time that you see uh, this formula for the update of the value functions, but it's not different from what I usually say. So I say that the for updating the value function, if you're using a tabular method, then you use your previous estimation plus alpha that multiplies the error, which is computed as your your target minus the previous estimate. And this is basically doing the same thing that is, except that this is done in parameter space. So it's just the same thing, which is what happens if you're doing an update, for example, by using a neural network, which is the procedure that I have described also in the other uh, in the previous classes. So note that I'm insisting on you asking questions on this because these will be most of the projects will be on policy gradient and actor critic methods. So um, please try to understand this. Also, we'll try to read some paper for the not maybe next class, but the one after. I'll let you know what will be the plan for the next class, depending on whether that is tomorrow or not. If it is tomorrow, we're not reading the paper. If it is directly next Monday, then we are reading the paper. But anyway, uh, this is very important to be understood. Note that so far we said we are assuming still, I mean, we didn't make any clear assumption how the policy was being represented, and we didn't say that the policy was discrete or continuous. Although if you are using a policy which is, when we are dealing with continuous actions, a practical choice in order to deal with large action space that are continuous is typically to use a normal distribution. So the policy is basically a Gaussian where you're sampling from. So your function approximator is estimating the mean and the standard deviation of uh, your policy. So that's why you have here mu of s theta and sigma of s theta. So if you're using a neural network here, your neural network will have two heads where, so two parts, the same neural network, but with two separate parts where you're estimating in one the mean, the other the standard deviation. So the set of slides is finished here, and again, I reserved more time for this class in order to answer questions and doubts, which generally, I mean, previous classes had questions on this part, so I wanted to make sure that this was clear. So please, if you have questions, ask them now. Don't wait for office hours for these classes, for these questions, because these are of interest to everybody. I've been trying to go very slow uh, for this class, for this specific topic. So again, I've been asked also to go more slowly for some of these topics. I'm doing that, but if you don't participate, the policy that is a Gaussian. So if you're dealing with a continuous action space, right, you don't have a specific action that you can select, right? So you need to do some sampling over there. And so in order to do this, you represent your policy in the form of a Gaussian, where you are approximating, instead of learning directly the action, you're learning the distribution of the action. Or in general, it's not say that it has to be Gaussian. It can be any distribution, but this allows to simplify a bit the problem, right? Because instead of having to compute uh, the probability of every possible action, you're computing the probability of some distribution. Sorry, not the probability of some distribution. You're computing the parameters of some distribution, which then will allow you to compute the probability of some action. So this is sort of simplifying the problem for the function approximator itself, right? Because it might also not be that relevant if you are taking action, I don't know, in a continuous action space where you are controlling directly the torque that is given to the motors of your wheels of the robot, for example. Then you don't care about maybe the exact value, but you want to also to explore during learning. So this is allowing you to explore quite easily, but on the one hand, but on the other hand, you also might not care too much whether that is the torque is 0 0.1 or 0 0.112 or 123, something like that. So uh, it's just simplifying the problem, allowing for exploration inside the structure of the policy itself, and at the same time, simplifying the problem if you have a large continuous action space. So you can imagine, in this case, that you have a function approximator, for example, let's say a neural network, which is predicting two things. One is the mean, and the other thing is the standard deviation. And then you compute your policy using those parameters. So you put on top of this formula, and then you will use this to do everything that you need to do. Okay, anyway, so the plan for the next lessons for me is to stop with the theory here. I will answer this question right after these comments that I'm making. So the plan for the next lessons for me is to stop with the theory and first of all do a short recap in the form of a table. So creating a table for you where describing a table for you where we put everything together once again. So a table where we are um, summarizing everything and clarifying. Maybe if you have questions, you can maybe go back uh, um, to your previous notes if you have them, and ask questions. So this will be next class, either tomorrow or Monday. I'll let you know later today. And to look at one example where I'm using a neural network, for example, to do Q-learning. Okay, that will be the plan for the next lesson. If we're doing it tomorrow, it will be just it. If we're doing it on Monday, we'll also start reading one paper, which is a paper that presents an algorithm which is at the state of the art. And in this paper, and that's the plan also for the next classes in general. I want to present you 2 to 3 papers where you are going to basically, I mean, this will be, uh, first of all, parts of your projects. I will not present all the algorithms that are going to be used for the projects, but they will be related anyway, so there will be not a lot of difference between those. So we'll explain papers that are related so that it should be clear also for those of you who get different algorithms. And we're going to look at these papers, trying to understand how they relate to what we have seen in class, and what maybe try to clarify some doubts that you have to understand something that is unclear. We'll also look at um, some example implementation of those, uh, also because the projects will be of 2 different kinds, actually 3 different kinds, but anyway, there will be projects where you will be just using algorithms and then doing some performance analysis of these algorithms. So if you can use, for example, OpenAI baselines where these algorithms are already implemented. Or the other thing is you will go in detail and start from scratch and implement your own reinforcement learning algorithm. I mean, one of these, of course. And of course, you will be able to rely on implementations that already exist online, but you will be implementing yourself, which is a completely different thing. So this is a project only for those of you who want to understand it in detail, and I expect nobody to do any kind of, again, of plagiarism for those, because again, it's not mandatory to do that. You can choose a different kind of project. Of course, every different kind of project will have a different maximum score, but that's the overall idea. Okay, so is there any way to exit from a local optimal solution? So one way to exit local optimal solution is to do some further exploration, first of all, and to collect more data. The other way depends on the optimizer. You can use some optimizers that have the notion of momentum and stuff like that, like Adam, for example. Some other optimizers that help exiting local optima. You can try to do some simulated annealing, which you should have seen in AI. Uh, these kind of things. So this is standard. This is a standard issue. Basically, every optimization algorithm has this problem. You will find the same issue in any setting where where you don't have a very convex function to optimize. So if in this case these functions are most of the cases are non-convex, so it's uh, easy to fall in some local optima instead of the global ones. Some other approaches which don't really apply a lot to reinforcement learning. I've seen few of them doing this, but not a lot. You can basically uh, transform your problem in a space where basically your function becomes convex. Again, in reinforcement learning, this is hard to do. I've seen few work doing this kind of thing. but again, this is another way to deal with this in general, not only reinforcement learning. This is also the problem of in general of one problem on machine learning, where I mean another way to do this, right, is to use over parameterized functions, where basically falling in a local optimum is much more complex because you have so many parameters that basically will allow you to move outside of this optimum. And this is basically why deep neural network have been so successful. Some people argue this, some other people argue the fact that there are so many parameters allow the neural network to find a very nice spot in the local optimum, in the local optima land. So that's the other trick. The problem is that with reinforcement learning, you cannot really go so deep, because going also deep means a lot of more data. And in reinforcement learning, that is a problem. How much bad is the local optimal solution with respect to the global optimal solution in general? It depends on the problem. It can be quite bad, or it can be nearly as satisfactory. It really depends on the task. There is not a general answer to this question, I would say. I have seen local optimal solution where it was acceptable basically, and other ones. So even if you look at if you remember when we started the course, I have shown you a video where there was this humanoid-like robot, let's call, or agent simulated, that was learning to walk, and it learned to walk by moving the arm this way. And that is not the global optimum, for example. That's the local optimum, but still seems quite satisfactory for some tasks, right? So that was a local optimum. Then you have seen that with more training, maybe more data, maybe some other tricks that they use, they have been able in the last few frames of the video to show the agent fully learning to run properly. But that was a local optimum, for example. Okay, so if there are no more questions, we can close it here, and I'll let you know for tomorrow. I'll talk to Professor Yoki. And yeah, then see you tomorrow or Monday.